let's talk a little bit more about the comparison between Sn1 and Sn2 reactions. And maybe we can also talk about what type of conditions make one or the other more favorable, and especially the solvent. We've talked about it a little bit, but we'll go into a little bit more detail. So just as a bit of a review, an Sn1 reaction, you might have some type of let me just draw it like this. So you'll have some carbon that's attached to three things. I'm making these three things just arbitrary colors. They could be other carbon, CH3, it could be hydrogens, it could be other things. And then it's also attached to a leaving group. Also attached, let me do this in a color that I haven't used yet, in pink. It's also attached to a leaving group. And then you also have a nucleophile. You also have a nucleophile floating around. That'll be our nucleophile. It has one excess electron, has a negative charge. And in Sn1 reaction, the first step only involves one of the reactants, one of the reagents. That's why it's called Sn1. So in the very first step, the nucleophile just waits passively while the leaving group leaves. So you have the leaving, there's an electron right there. The leaving group already has an electron. It swipes one. So it has to be reasonably electronegative. It swipes one from that carbon. And so once it does that, our situation will look like this. You have your substrate. It now just lost an electron. It lost that electron. So it now has a positive charge. I have that little trace of something. Let me erase this right here so you don't think that electron is still there. So it now has a positive charge. The leaving group, which was neutral, took an electron, so it now has a negative charge. The leaving group now took an electron, so it now has at least two valence electrons there. It has a negative charge, probably a lot more. And then in the next step, this nucleophile, so let me copy and paste this. No, that's not what I wanted to do. Let me copy and paste it again. So copy and paste. OK, so that thing that was waiting patiently during the rate determining step says, hey, there's a carbocation there. I'm a nucleophile. I'm not a strong nucleophile in the case of an Sn1, but I still like giving away electrons to nucleuses. I love nucleuses. I see a positive carbocation there. Well, actually, a carbocation is positive by definition. So let me give my electrons to him. So let me give my electrons to him. And in the very last step, we have a situation where this guy, let me copy and paste this again. Let me copy and let me paste. That guy is bonded to the nucleophile. Since the nucleophile gave the electron to this carbon, the carbon doesn't have a charge anymore. And since the nucleophile lost that electron, it's now neutral. So you have it bonded to the nucleophile. And of course, you have the leaving group still here. The leaving group still here with a negative charge. And we've hinted at this a little bit. But in order for this step to happen, with kind of on its own, with only this reagent happening spontaneously to some degree, or for it to just happen, and we won't talk about the rates, and it won't necessarily happen fast, but in order for this to happen at all, this has to be a stable carbocation. And we've seen before that in order for this to be a stable carbocation, it has to be bonded to things that are willing to lend it some electrons, so that it doesn't, so it's not super hungry for electrons. And in order for that to happen, this carbocation right here has to be tertiary. Tertiary is ideal. And tertiary carbocation means that these three things over here are all carbons or carbon chains. So ideally, it would be tertiary. And secondary will also work if at least two of these guys are carbon. That'll also work if the solvent is favorable, if the environment we're dealing with is a favorable environment. If only one of these were carbons, so if this is a primary carbocation, or if this was a methyl carbocation where nothing here is a carbon, then you're unlikely to have an Sn1 reaction. Now, on the other side of the picture, Sn2 reaction, this is the one where you have a super strong nucleophile, or at least a strong nucleophile. And the whole reaction happens in one step involving both of the reagents. So you start here. You with you have your leaving group. The way you can think about it, Sn1, the leaving group is the thing that does something first. In Sn2, it all happens at once, but the nucleophile is kind of the aggressor. It really wants to give away. It really It really wants to give that electron away badly. So in the very first step, it comes in here and gives it to that carbon, even though that carbon didn't necessarily want it that badly. It would have a partial positive charge. If this thing is really electronegative, it might be hogging this electron already. But that thing that it was already hogging, now it could say, hey, you already got an electron, I can take it from you. And so in literally one step, we end up with something like this. Actually, let me just redraw that. So we have our leaving group has left. It's taken the electron that the carbon didn't need anymore. So it now has this electron and that one, and maybe more. And it has a negative charge. And now this carbon, it's attached to the blue thing. I'll just draw the purple thing. And maybe in back, it's attached to the orange thing. Let me draw it so you see what I'm talking about. So the blue thing and then the purple thing. And then the nucleophile had come from the other direction, so now it's also bonded to the nucleophile. The nucleophile is giving an electron, so it loses its negative charge. And essentially, the negative charge gets transferred to the leaving group, which is able to take an electron, and then that carbon in the middle stays neutral. And we saw before that this can only reasonably happen with a strong nucleophile. That has to be a strong nucleophile. And there can't be a lot of steric hindrance. These things can't really block this nucleophile from attacking. So this will work best if this is a methyl, or primary carbon. And if the conditions are just right, and if the nucleophile is strong enough, maybe secondary. Maybe a secondary carbon. Because once you have too many carbons or big carbon chains over here, then it blocks the nucleophile. It cannot attack. If these are all hydrogens, there's a lot of space for this nucleophile to attack. If only one of these are carbon, still a lot of space. Now, that's just a kind of a general comparison. And it gives you some clues. Weak nucleophile, you're dealing with Sn1. Strong nucleophile, Sn2. If this is a tertiary or secondary carbon, so if it's bonded to a lot of other carbons, Sn1 should be in your brain. If this isn't bonded to a lot of carbons and you have a strong nucleophile, Sn2 should be in your brain. And now the last thing you should have to think about is the solvent itself. What are these reagents actually dissolved in? So let's think about it. So we definitely, in either an Sn1 or an Sn2 reaction, we're dealing with things that have charge. And in general, if you're dealing with ions or things that have charge, they're going to be more soluble in polar solvents, because the charge likes to be around other things with charge so that they can mix and match. So in both situations, you want to have polar solvents. Polar solvents in both situations. And you are familiar with polar solvents. Examples of polar solvents are, well, water is a polar solvent, H2O, and it's polar because oxygen is so electronegative, it hogs electrons. So you have a partial negative charge on the oxygen side and partial positive charges on the hydrogen side. Another example of a polar solvent that you may have not seen before, is something like diethyl ether. So diethyl ether would look like this. CH2, CH3, CH2, CH3. And I know we haven't named ethers yet. Let me write this. This is diethyl. Let me make sure I get that Y right. Diethyl. This is diethyl ether. And just as a bit of a reviewing, this is probably the best way to learn things, as we learn as we go. An ether is something that has the form. You have some carbon chain or some, you could call it a radical, some group attached, a carbon chain, I guess is the way my brain processes it, to an oxygen which is attached to another carbon chain. It doesn't have to be the exact same one. In diethyl ether, it is the same. And you're literally just saying diethyl. You have two ethyl groups attached to an ether. Ethyl is two carbons. So two carbons, oxygen, two more carbons, diethyl ether. And this would also be a polar solvent because oxygen is more electronegative than carbon. So you still have this partial negative charge. Let me do this in a different color. On the oxygen end, you still have your partial negative charge on your oxygen end, and you still have a partial positive charge on your carbon end. So this is also a polar solvent. Both of these are polar solvents. Now the difference between these, and this will probably be a new term for you, is this water and most types of alcohol, some things that have hydrogens that could be knocked off, this is a protic solvent. This is a protic solvent, and protic just comes from protons. And that means that if something is dissolved in this, or if you have a solution of this, that these hydrogens might be able to get knocked off, and you might have free protons lying around. Because if, let's say, this oxygen swipes this electron from this hydrogen, if it swipes that electron from that hydrogen, then you have a situation where you have OH minus, right? The oxygen now has a negative charge. And this hydrogen, all it had to its name was that electron. If you take that away, all it is a proton. So when someone draws H plus, that literally is a proton. That literally is a proton. And this can occur in water, that you have some protons floating around. So water is fundamentally a protic polar solvent. Diethyl ether, on the other hand, it doesn't have hydrogens that where oxygen can take its hydrogens away. The hydrogens here are all bonded to carbon, which is not that electronegative. So this is an aprotic solvent. Let me draw this. This is an aprotic solvent. Now, let's think about whether an Sn1 or Sn2 is better in. Well, I already said they're both good in. The solvents have to be polar, and that's because we're dealing with charged things in both reactions. But which one will be better? So let me write this down. So in both situations, we want a polar solvent. So let me write that down in both situations. And I'll give you a hint. One of them will be good in a protic environment, and one of them will not be good in a protic environment. So in an Sn2, if you had, let's just think it through. Let's just not memorize this. If we had protons floating around, in an Sn2 situation, what is likely to happen? We have this strong nucleophile. We have this thing that wants to give away electrons. Now, it could give it away to a carbon that might maybe have a partial positive charge, then the leaving group could take it away. But what wants electrons more? A carbon that has a partial negative charge, or a proton, something that has a full positive charge? Well, a proton would want it more. So if you had protons floating around, the nucleophile would just give its electrons to the proton, and the Sn2 reaction wouldn't actually occur. The protons would take all the electrons. So you can't have protons floating around. You cannot have protons floating around in an Sn2 reaction. Then this carbon will never get the electron. The proton will take it. So you need an aprotic. You need an aprotic solvent. So Sn2 would work well in diethyl ether. If this is a strong nucleophile, it's a solution in diethyl ether, and this were all hydrogens, then you'd be just ready to go for an Sn2 reaction. Now on the other end of the spectrum, the key in an Sn1 reaction is that this carbocation be stable. And for a carbocation to be stable, or actually even more important, instead of the carbocation being stable, that's dependent on it being a tertiary or secondary carbon. But in order for the leaving group to be stable when it's negative, it actually would be nice if there were some protons available. Maybe it could give electrons to the proton. Maybe it could bond with the proton. So in this situation, the protons will actually help stabilize the situation. So in an Sn1 reaction, the ideal is actually a polar protic solvent. So if you see a situation where you have a secondary or tertiary carbon, it is a weak nucleophile. You have a weak nucleophile. And you're dealing with a polar protic solvent, the most famous of which is water, but an alcohol would also work, then you should be thinking Sn1. If you see a strong nucleophile, there's not much steric hindrance. There's space that it can attack. This is a methyl or a primary, maybe a secondary carbon, and it's happening in an aprotic polar solvent like diethyl ether, then you know you're ready for an Sn2.